Okay, great. So thanks to the organizers for the invitation to speak. Sorry about the mix-up with times here. Let me just write my talk title. Okay, so my talk is about cyclic homology and S1-equivariant symplectic cohomology. These are both, in a sense, S1-equivariant theories. Cyclic homology is, of course, taken with respect to something, so I'll say what that something is. It will be the Fukaya category. And this is some S1-equivariant theory constructed out of a type of Hamiltonian Flur homology. So the goal will be to relate these two. So to study S1 actions in Flur homology and show a certain open-closed string map, which I'll put in quotes because I haven't said what such a thing is S1 equivariant in a suitable sense, which will imply some sort of relationship between these theories. Okay, so what do I mean by this? Well, let me talk about the notion of S1 equivariance first. Okay, so maybe let's just recall S1 actions in topology. Okay, so let's say we have X a space with S1 action. Well, it's a very old observation at this point that if you take the quotient by the S1 action, or equivalently the fiber product over S1 with a point, where a point has trivial S1 action, and take its homology, it's sort of a bad invariant. Okay, so it's not a homotopy invariant of the data. Okay, so it's poorly behaved. As a homotopy invariant. Okay, so the solution, of course, is, comes from the Borel construction, and the solution is to sort of really think of the quotient via this construction, X fiber product over S1 point. The reason this homology group is poorly behaved is because point is a bad space from the point of view of, S1 topology. You should replace point by some equivalent space. Which is called ES1, on which S1 acts freely. And so this is some contractible space with free S1 action, so it's homotopy equivalent to point. And now you can define that fiber product. The homology of that fiber product will have better properties. So you can define the equivariant homology of X to be the homology of X fibered over S1 with ES1. Okay, and so the relevant properties for us are the following. So the main one is homotopy invariance, and by this I mean the following. So if we have a map of topological spaces, let's say each of the spaces has an S1 action, and this map itself is S1 equivariant. It induces a map of equivariant homology groups, which is an isomorphism if the ordinary map between homology groups was. Okay, so it's an isomorphism if this map is an ordinary homotopy equivalence, but it's also an isomorphism if the map was just a homology equivalence on regular homology. So it somehow says if you want to sort of show that equivariant homology theories are isomorphic, what you really need is an equivariant map, and then you have to check something on just ordinary homology. Okay. And of course, this has the property that if the other defining property of equivariant homology is that if S1 acts freely on X, then our original prescription was actually the right one. So these can be taken as a characterization of equivariant homology in this setting. Okay, so the main observation from topology that I want to bring in is that actually we could have constructed this equivariant theory from chain level data. Okay, so we can construct equivariant homology from chain level data. What do I mean by this? Well, singular chains on X is a module over singular chains on S1 from the S1 action. Singular chains on S1 has an algebra structure via the Pontryagin product, so you can talk about a module over it. And the singular chains on the Borel construction, some fiber product. It's sort of known from algebraic topology that this is just a tensor product over this algebra of singular chains on X with singular chains on ES1. Okay, but let me point out that singular chains on ES1, since S1 acts freely, singular chains on ES1 is in fact a free chains of S1 module. And ES1 is contractible. The map between ES1 and point induces a quasi-isomorphism of C star S1 modules from this to C star point. So you should think of this as a free resolution of C star point, right? Okay, all of which is to say that you can think of this in a more abbreviated fashion as a derived tensor product. So to compute this, we replace this by a free resolution and take the tensor product. Or if you want, equivalently, it's a Tor. And now I'm just using K instead of C star point because these are equivalent. Okay, so I started with a space with S1 action, but from that I can extract a module over chains on S1, and that's enough to recover equivariant homology. Okay. And why do we need this? Well, we're going to study contexts where there aren't geometric S1 actions, and so sometimes we'll want to construct equivariant homology this way. So let me make a definition. Now I'm going to switch notation from chains to cochains. So bear with me for that. So let's say we have a cochain complex. We say M carries a strict S1 action if M is a unital differential graded C star S1 module. Okay, and since I'm working cohomologically, I have to reverse the grading of C star S1. So this thing, let's just remember, is actually equivalent as an algebra to K join a variable mod beta squared. Beta is the fundamental class of S1, so it has degree -1. Okay, so a strict S1 action is some module over this thing, and this is of course equivalent to the data of just a map. Okay, so this algebra has two elements, and one of them acts by the identity. So there's only one interesting map. So it's just a map, which I'll call delta. This is multiplication by beta. And it has degree -1 if the differential has degree +1 with, well, it's a chain map, and it squares to 0. Yep. No, I'm cohomologically grading it. I'm just negatively grading it. Absolutely. Yeah. Yeah, so the example of such a thing is negatively graded singular chains. No, it's just convenient for the conventions that follow. You could set it all up positively graded. Okay, great. Oh yeah, and definition 2, if I have a complex with strict circle action, I can define the equivariant homology of M to just be this tor. And let me finally note, there's a small complex that computes this. So ES1 has a nice, one way to say it is has a nice S1 equivariant cell decomposition, so I can use cellular chains on ES1. Another way to say it is that K has a very small resolution. So using the fact that K is equal to the following resolution, I just have a copy of chains on S1 and multiplication by beta, so I just infinitely many copies. So K equals that. That means tor with M and K is just the actual tensor product over chains on S1 of M with this, which I can just write as a very explicit collection of copies of M. So let me just write it. So we have just negative. Well, what is this? This is Laurent series with no positive part. So it's polynomials in U inverse if you want. With this differential. So U here is just a formal variable keeping track of all my different copies. Okay, so this is just some very explicit complex you can compute for equivariant homology, but there are others, so on. Okay, so algebra aside, let's talk about how this is appearing in Flur homology. Okay, so let's start with an exact symplectic manifold. And assume it's Liouville, so it has some convexity condition at infinity. I don't want to go into what it is. Or we don't need to assume exact. We could assume some other standard hypotheses in symplectic geometry. But maybe let's work with the exactness condition to make a definite statement. OK, so let's say I have a setting like this, and I pick a function Hamiltonian. Then, of course, I have the Hamiltonian Flur complex of H. OK, so it's the Morse complex, very formally. It's the Morse complex for some action functional on the free loop space. You can even write what it is. So it's not too relevant, at least for the discussion I want to have today. OK, so we have some explicit complex. Of course, I have to choose as in Morse theory, I have to choose a metric to get a Morse complex. So here I have to choose an almost complex structure to get the differential. Let me just finally say what the generators are. So critical points of this action functional are time 1 orbits. OK. Just reviewing what this complex is. And finally, gradient flow lines in the loop space are equivalently maps from cylinders into M, satisfying the gradient flow equation well. For the action function. OK. I don't want to talk about specifics at the moment, but let me just point out schematically, so we're taking some sort of homology of a space. It's not the usual homology. It's some homology given by this very special function. It's an infinite space, but that's not too important from this perspective. The important thing is this space has an S1 action. Okay, so S1 acts on the free loop space, of course. By shifting loops. And so we expect that there exists a chains of S1 action on this Flur complex. Okay, and well, let's just define it, right? So let's So I said before, we're going to run into the first subtlety in a moment, but this is naively stated as such. There's going to be some problem, but let's just try to go forward and see what happens. Of course, so what we need supposedly is just this operator satisfying some conditions. So let's define it. So for orbits xy, let's define the matrix coefficient delta xy by counts of parameterized moduli spaces. Okay, let me actually, before I continue, sort of say that this approach to defining the S1 action, let's see. So parameterized moduli spaces, I think, were used in a different setting first by Hutchings. This approach has been, suggested at least briefly by Seidel in his biased view survey on symplectic cohomology. And also by Bourgeois and Oncha in their recent preprint. Okay, so what is the parameterized moduli space? I'm just going to look at the space of pairs, theta in S1, and U a map from the cylinder into M with asymptotics x and theta pullback of y, satisfying a gradient flow equation in this region for the usual action functional. In the bottom region near theta pullback of y, it's going to satisfy a gradient flow equation for the theta pullback of the action functional, which, as I've defined it currently, is just the gradient flow of the action functional itself. And in this region, there's some interpolation. Okay, so the first remarks. So this gives me some parameterized family. I can count its rigid components, and I get some matrix coefficients, and I can define an operator. Yeah, H is invariant under. What maybe the right thing to say is the action functional is invariant under rotation, as I've defined it. And I'm implicitly assuming, I'm implicitly assuming that the metrics also, invariant under loop rotation, which is one of two lies I've told in this so far. Maybe now's the right time to, okay, so let me start with a fake lemma and then just say why this is not quite right. But, okay, so the claim, this is actually a well-defined operation. Okay, so the claim is that still we have a chain map. Okay. And it should give a strict S1 structure on the Flur complex if things could work out the way I naively stated them. Okay, but what's the problem? You know, even in Morse theory, sometimes there's a problem, I think, which is that, of course, if you have a space with some action, well, maybe in Morse theory it's okay, but here you sort of, well, let me just say what the problem is. Okay, so we cannot, in reality, guarantee that either the action functional for which we are really taking Flur homology or the metric are S1 independent. Okay, so in general, to actually get a non-degenerate critical points, a non-degenerate moduli space, we have to consider S1 dependent. J and H. Orbits of H come in S1 families, right, as I define them. So thus, orbits are degenerate. They're not non-isolated critical points, so we break S1 symmetry and study the Flur complex of H plus some S1 dependent perturbation. Okay, and similarly, we really need some S1 dependent almost complex structure. Okay, all of this is to say that we get a chain map, but it doesn't square to 0. Okay. But, well, it's a chain map, and you can show that in homology it squares to 0. So in particular, delta d plus d delta, delta squared is chain homotopic to 0 for some explicitly constructible chain homotopy. Okay, so suggest maybe we should modify our definition if we want to talk about S1 actions in this setting. Okay, so the definition 2 is that of a weak S1 action. So M has a weak S1 action, or maybe you could say A infinity S1 action. If M is an, well, let me state a definition and then just explain what it means concretely. So if it's a strictly unital A infinity module over chains on S1, which I'm, for concreteness, using this very particular model of chains on S1. Okay, what does this really mean? It just means, let me translate this into sort of, this language. So what sort of operators do we need and what relations do we need to satisfy? This just really means we have a map delta lower k for each k greater than or equal to 0. It's a map from M to M of degree 1 minus 2k, with delta naught just being the differential, delta 1 being the delta map we defined before, and generally delta k you should think of, if you like A infinity modules, you should think of this as, there's only one interesting operation at each level. An A infinity module allows you to multiply by many copies of chains on S1. So you have many copies of chains on S1, a single copy of M, you get a copy of M as an output, and so there's only one interesting thing to specify, which is how you multiply by k copies of beta. Right? And this is the thing that's supposed to correspond to delta k. And what equations do they satisfy? Well, they satisfy d squared equals 0. Delta is a chain map. And the next equation it satisfies is what I wrote down. So delta squared equals d delta 2 plus delta 2d. OK, and higher coherences. Let's not worry about them for the talk. So why is this good news, actually? Even though it's a mess of things to keep track of, the good news is that weak S1 actions have nice equivariant homology theories. Okay? So let me note, there is still a well-defined equivariant homology theory. And since this is a type of module, you might believe that because maybe it has a nice notion of Tor, but let me instead give an explicit complex that computes it. The equivariant homology of this complex can be written in sort of much the same explicit way as before. We look at just direct sums of copies of M, indexed by this formal variable with negative coefficients, and the differential equals d plus u delta plus u squared delta 2 plus u cubed delta 3. OK, so this is some infinite series, but on this quotient, this is sort of a finite operator on each point in this. Yes?
Is there some kind of a homology setting like that where these S1 modules is kind of equivalent to the usual category?
Sure, yeah, absolutely.
There would be a different presentation of this cohomology that we're kind of strict.
Absolutely, and I think that's sort of what you see in A-infinity algebras too, but the reason you want to stick with these weak complexes is that's really closer to what's actually happening in geometry. Like these operators are actually being defined by some counts, and it's convenient to stay with them. I mean, another thing to say is this transfer ends up involving all of these operators anyway. So. Yeah.
So over here you intend to define a chain map delta, right?
Yes.
That's what we were sort of hoping was.
Actually, is a chain map.
Sorry, not chain map. I hope you define a differential or a co-differential.
Yeah, so like a sort of something that squares to 0. That's right.
So that's what you're looking for. But
yes.
We say if we actually carry things through, we find out problems, and it turns out that we can't use this to define a differential, right? This is sort of what happens. And so then from there, this is sort of what led into sort of whatever you're doing on the lower left-hand board there.
Yeah.
So I just want to back up to ask sort of a
Great.
really trivial question.
Wonderful.
Here.
Yeah.
So
I'm glad to hear it.
A closed manifold, for instance, with an S1 action on it.
Mm-hmm.
Is there a standard procedure for defining like S1 equivariant Morse homology just for this? Right?
Yeah, absolutely. In fact, what I've said actually is completely, you could have forgotten you were working in the loop space. I mean,
right.
the point is what you should recover if you just pick a random Morse function and a random metric that has nothing to do with the S1, it's not S1 invariant or something. You should get a weak S1 structure on the Morse complex, and you should be able to define the Morse homology the exact same way.
But I mean, if there's no way, so maybe you start with your fixed Morse function and metric, and they're not S1 equivariant, but now you do, S1's nice and smooth and compact, and so I can do an averaging procedure.
You can average, that's right.
Now I've got a nice now I have sort of a nice setup where I might expect to be able to, if I were really lucky, presumably you can actually define S1 equivariant Morse homology, but you would want, you need certain transversality of stable and unstable manifolds.
Exactly.
Which in general isn't going to happen.
Exactly.
So what I was just sort of wondering is there sort of a, potentially a perturbation theory? I mean, for instance, there exists Morse homology for orbitals. Where you have sort of finite group actions sort of acting locally, and these you have sort of finite set value type perturbations which would allow you to recover the correct homology at the end of the day. Is there anything like this for like an S1 case, just in finite dimensional stuff? No
and that's not a trivial question at all, I don't think, by the way. But I have not thought about it. I mean, I would presume there is, but it's a question more for you guys, perhaps. I actually haven't thought about it. I mean, somehow through thinking about this, in Flur homology, which was the main example of interest to me, there are already sort of issues are so severe that you kind of need to go this weak S1 route. So,
I mean, I only ask because because the direction that you sort of have to take with this, you have to say, well, we need to, I don't know, we need transversality leads to something like it's like you have to break symmetry, and then you're sort of, and then it's natural for you to sort of walk into this much more, algebraic sort of framework. But you lose so much symmetry. I mean, it'd be nice to be able to preserve some of that a bit further.
Sure. I mean, for instance, well, I think if you want to get something like equivariant localization off the ground in Morse theory, you probably want some symmetry. But I mean, I agree with you. I think there are reasons to have symmetry. I think that helps a lot with computation, for instance. But
okay, very good.
yeah, no. I mean, but no. I think it's a very interesting point. I don't have a good answer for you at the moment, but perhaps afterwards. Okay, so we, at the end of the day, we end up with this structure. It's some slightly more complicated structure, but it's completely geometric. It's just given by some, some counts of maps that look like this, and time permitting later, I can write down a prototypical example like delta 5 or something. You see what exactly is going on, but. And we have a well-defined equivariant homology theory. And there's a alternate approach to equivariant homology. Maybe this is studied by Viterbo and Bourgeois and Chea, which is that instead of just looking at the chains on S1 action, or looking at these parameterized moduli spaces, instead, why don't you just take Flur homology for the Borel construction? I was not aware of that. I mean, I think it's an old idea. Yeah. Very nice. So yeah, it's an old idea to want to do, and it's very natural because, of course, this has an S1 action. So you might try to treat it as a space and then, pass to, Flur homology type theory. It actually turns out, I think this is, well, let me just say that these lead to equivalent answers. Okay, so there's no issue. And I think this was discussed in Bourgeois-Uncha's recent preprint. We get the same answer. Okay, but there's perhaps a real reason to study this perspective on S1 equivariant homology coming next. Okay, so this is the structure we get on Hamiltonian Flur homology. Okay, actually my talk title had the word symplectic cohomology in it and not Hamiltonian Flur homology. So maybe I should just point out that it's a type of Hamiltonian Flur homology for a specific Hamiltonian. And that's sort of the extent to which I want to So it's Hamiltonian Flur homology for sort of class of large growth Hamiltonians, which only makes sense on a non-compact manifold, or it's only an interesting class or different class on a non-compact manifold. And the equivariant homology of this is interesting and related to contact homology. Okay, let me switch gears and talk about another S1 action. On Lagrangian Flur homology. Okay, so let's say we have a pair of Lagrangians. Then we can define, let's say they're exact again, or monotone, or something. And in nice cases, we can define a chain complex with a differential called the Lagrangian Floer homology, and it's again formally a Morse complex. And it's a Morse homology type complex for essentially the same action functional. But this time, instead of from the free loop space of M, we look at the space of paths. Okay, well, I said I would talk about circle actions. Free loops have nice loop rotation actions, and paths obviously don't. Okay, so let's note there's no obvious S1 action on paths. But if I take some cyclic products of paths, so if I take paths from Lk to L naught, followed by paths, there's always some convention, paths from L naught to Lk, followed by paths from Lk minus 1, Lk, followed by paths from L0 to L1. So this is a chain. So I take a collection of Lagrangians. I take the union of path spaces between Lagrangians, sort of all cyclic paths. Okay, so if I take this kind of very large space, yes, thank you. Absolutely. Great. So I should think of an object of this set as sort of some chain of paths like this. Okay, so this thing, well, it doesn't have an S1 action, but it has a discrete action. It has a cyclic action. Okay? Z mod k plus 1z. Okay, and so there's an old algebraic observation, not special to Floer theory at all, and first observed in other settings by Kahn and Segan, that if you have the data of cyclic, finite cyclic actions for kind of all values of k, this leads to a circle action on a certain complex. Okay, so these can be packaged into a chains of S1 action on a certain complex. So these Z mod k plus 1 symmetries can be packaged into a chains of S1 action on some big complex. We define, well, okay, let me sort of point out, just for notation, that this Floer complex for a pair of Lagrangians can be regarded as a morphism space in a category called the Fukaya category. I don't want to say any more about it yet than just say this is what its morphism spaces are for Lagrangians, which are objects. Okay, so it can be packaged these cyclic symmetries can be packaged into a big chains of S1 action on Hochschild complex, okay, which very explicitly it's some invariant of our category, which is really consists of some big direct sum of Flur complexes corresponding to every one of these path spaces. Right? Okay, and what I didn't mention about the Fukaya categories, of course, there are some compositions and maybe some higher compositions, and so there's some interesting differential on this big direct sum that comes from summing over ways to contract morphisms around a circle using compositions. Okay, so differential involves applying compositions in F to contract. Okay, so I can say very specifically what the delta operator is in this case. Well, I have to define some intermediate operations. So there's one operation called T, which is the cyclic permutation operation. So T, so what's an element of this big direct sum? It's some, you could think of it as generated by some tensor product of time one paths of our Hamiltonian. And the T operation just hits this collection with a once around cyclic permutation. N maps an element to the sum of all possible ways to cyclically permute before you, so the sum over all multiples of this operation. And there's an operation called S. So these operations preserve the length, the number of letters in the word, and S increases the length. So it inserts an element at the beginning. The element is some, it's a unit. So units, so we're assuming units exist in the Flur complex of x with x for any x. So supposing units existed, which actually this is the next subtlety that I'm going to skip over today, but there's some issue with what I just said, that units may not exist naturally in the Fukaya category. But there are homology units, and so imagining you had nice units for the Fukaya category, this S operation would just insert a unit. And then delta, the delta operator, which is often called B in the literature, is just 1 minus Tsn. Okay? And the lemma is this defines a chains on S1 action. Strict. Actually squares to 0. Okay, so now we get to the other term I mentioned. in my talk title, let me just say quickly that the cyclic homology is the equivariant homology for this action. Okay, cyclic homology of this category is the equivariant homology of the Hochschild complex using this chains on S1 action. Okay, so it's something. Okay. So there are maps relating these two, which are in many cases expected to be isomorphisms, some cases known to be isomorphisms. So I think first constructed by Seidel and Fukaya Ota Ono, though we're using a version I think first appears in work of Muhammad Abu Zaid's. So there's a map from the Hochschild chains of this Fukaya category, which is this big direct sum, to the Flur complex, the Hamiltonian Flur complex. Okay, and so how does this map go? Well, I have to tell you the matrix coefficient of this map. So given a cyclically composable sequence of chords of a Hamiltonian and an orbit, I have to give you a number I'm being deliberately vague about this. So what should I say? So symplectic cohomology is the Hamiltonian Flur homology for a particular class of Hamiltonians. The wrapped Fukaya category is the Fukaya category for a particular class of Hamiltonian, allowing non-compact Lagrangians. I think that's the most abbreviated way to say it. But you know, a lot of what I'm going to say applies for the compact category, or so I'm trying to omit that point and just focusing on the fact that these are defined using, you know, Flur's equation for some Hamiltonian, and we can talk about whether the Hamiltonian is a large growth Hamiltonian, and in particular is something on the wrapped category. Okay, so it involves counts. Of the form, well, let me just draw a picture. Okay, so I'm going to take, conformally what I'm going to do is I'm going to take a disk with k plus 1 boundary mark points, one for each xk, and one interior mark point. For y, I'm going to puncture this disk and think of this disk as having, you know, some infinite strip-like ends near each of the boundary punctures and an infinite cylindrical end near this puncture. And I'm going to look at maps from this into M, sort of interpolating between the gradient flow equations. Okay, so it's going to, near one of these strips, it's going to solve a Fleur's equation, you know, for the action function on the path space between some given Lagrangians that we specify these boundary components to map to. So maybe the right thing to say is I'm going to look at maps from this punctured surface into M, whose boundaries lies on the Lagrangians that these morphisms belong to, satisfying some gradient flow equation that specializes to Fleur's equation on each end, and with the correct asymptotics. Okay, so I can define such a thing. I get a map, and so now we can get to the main point. Let me state a couple theorems and well, depending on how we're feeling, I know I started late, but I'm happy to stop early, near on time, or go a little further. It's once I state theorems, I'm at a stopping point where I can explain a few things. Okay, well, so the first theorem is that, okay, so we can ask what happens if I apply my circle operator before versus what happens if I apply it after. Step one, right? So the answer is, well, they're not going to be equal on the nose, but they're going to be chain homotopic. Okay, in particular, on homology, it'll intertwine, right? Okay, in particular, we can, maybe the right thing to say is there exists a map, OC under 1, from Hochschild chains to Hamiltonian Flur chains with DOC plus OC1D equaling the difference, right? So there's some explicit chain homotopy. Okay, so this already tells us maybe as an added remark, in many known cases, OC is an isomorphism. And so this already tells us that we, can replace this geometric count of parameterized moduli spaces by something, by some algebraic calculation if we understood one of the sides better than the other. But maybe let me state the second theorem, and then I'll explain the first theorem, and I'll explain a little bit of the first theorem and stop. Okay, so theorem 2 is, of course, that the way I've written OC1 should be, well, it is meant to be suggestive of the fact that there should be OCKs. So they're higher corrections. Okay. There exist higher corrections, OCK, so for each k greater than or equal to 0, from the Hochschild homology or the Hochschild chains to the Flur cohomology, satisfying, so with OC sub 0 equals OC, OC sub 1 as before, satisfying a hierarchy of equations, which I want to argue corresponds to the analog of having an equivariant map of spaces. Okay, so getting back to the original point, this sequence of higher corrections is the thing that should give us a map between equivariant homology groups. So let me just say the hierarchy of equations boils down to the fact that if you consider a big OC map, which is the sum of OC sub I u to the I, as a map let's see, 1 second. So as a map from the first equivariant homology group to the second, it's a chain map. Okay. Remember, the second has some interesting infinite series differentials. So the fact that this is a chain map translates into interesting equations for each coefficient I. Okay, so the corollary is that there exists a map an S1 equivariant map OC from the cyclic homology of the Fukaya category to the S1 equivariant Flur homology of our choice of Hamiltonian that is an isomorphism whenever the original map is. Okay, finally, maybe let me say just one word about the proof of Theorem 1, and then Theorem 2 is some higher corrections of Theorem 1. Actually, strictly speaking, this picture was not quite right. This picture is maybe the more correct one because here near the orbit y, I've specified a start point. So I need a framing for the interior point. And so one picks the framing by specifying that it should point towards the first point. You know, so each cyclic chain of words has a start point. And so we specify the start point of our orbit by saying it should point there. So we can define an operation where the position of the start point varies. So this operation is going to be controlled by the space of disks with boundary mark points and one interior mark point as before, and now in another interior mark point. And that other interior mark point is not going to serve as sort of an asymptotic condition for our equation, but it's going to, this mark point's free to vary around, and the asymptotic marker at this first point has to point there. Okay, and I'm going to count such elements. Now, my claim is it gives me a chain homotopy. And how am I supposed to see that between the two circle actions? Okay, so what's the codimension 1 boundary? So maybe let me just say free to vary. The formal marker. So the equation I'm going to solve is going to be different because when this point points in this direction, I'm going to be solving the gradient flow equation for this angle rotated Flur's equation. That's, okay. In codimension 1, we have the following breakings. So there's this formal marker could go to the boundary somewhere. Okay. Generically, it's going to land on one of these intervals. It's not going to land actually on one of these boundary mark points generically. And so we'll get a sum of terms that look like this. So it's sum over I. Where I'm counting things where I'm looking at disk with boundary component, and there's an additional mark point on the boundary between xi and xi plus 1. So it can land kind of anywhere on the boundary, and I'm looking at my asymptotic marker pointing at that thing. claim that this is actually, well, this is pretty close to the con-B operator. Okay. This is the con-B operator. So why is that? Well, this is a condition that's not serving as a boundary condition. Another way to say it is serving as a boundary condition, but we're constraining the point at that mark point to live on the fundamental class of the Lagrangian, which is not a constraint at all. And it's known that the fundamental class of the Lagrangian is supposed to be like the unit in Flur homology. Okay, so that's sort of roughly why this is like, saying that we're imposing a unit constraint and thinking of it as part of the cyclic chain. Maybe I'll just say that. Okay, and finally, there's this formal point goes to the interior, goes to the other mark point. Normally in codimension 1, that wouldn't happen in the ordinary Deligne-Mumford compactification, but because we're keeping track of asymptotic markers, you can see via a limiting process that the usual Deligne-Mumford compactification isn't right. The equation that you're approaching in different radial directions is not the same equation, so you actually need to perform a real blow-up of Deligne-Mumford compactification. So there actually is codimension 1 boundary as you approach this mark point. So we get a real blow-up of the Deligne-Mumford compactification. Hence, codimension 1 boundary. And what does the boundary look like? Well, let me just say this way. We bubble off a sphere where somehow there's this point that's free to vary around, and the asymptotic marker of the mark point that bubbled off has to follow that mark point around. I mean, I'll just say that vaguely, but it ends up looking like, it's conformally equivalent to a cylinder where one asymptotic marker is rotating and the other one isn't. And this is exactly the way we defined the delta operator. Okay, thanks. I better stop there.